Hello, this is Miraj Patel here, and today we're gonna begin talking about our last unit. So, good job for you. You've made it through the whole year, and we're at our last topic, and it's gonna be all about circuits, but in focus of DC or direct current simple circuits. And so here we're gonna first introduce what circuits are. And circuits are pretty much a path for electrons to flow in a complete circle or a complete, you know, um, complete cycle, sort of. And so uh, there's these things called schematic drawings of circuits. And so if we have this one simple circuit here with a battery, wire, and a light bulb, and it just comes right back, a schematic of the circuit would be like this. And so here we have a battery, which is represented by these four lines. And then we have a resistor, or the appliance, or the light bulb in this case. So a resistor is just a little squiggle like this. Battery's a set of lines like this. And the battery, the short side is negative, but it does not matter which side is which, because um, it does not matter how you solve the problem, positive or negative or positive. Originally, uh, Benjamin Franklin, he thought that the charge flows from positive to negative, but we all know that electrons are negative, so the negative side is what actually releases electrons, and it goes to the positive side. But it does not matter how you label it, but just as a fun fact, the 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 shorter side is the negative side. And then so there's three things we want to know when we're dealing with circuits, and those three things are voltage, current, and resistance. And a good analogy with electricity is just water flowing. So if you are good at or if you have a hard time understanding electricity without the analogy, just use the analogy. It's so much easier to think about it in terms of water flow. So voltage, just like in water, is sort of like the pressure behind the water. So how hard is it coming out? So like a fire hose, if it was a circuit, it would have a lot of voltage, but a house hose, just a garden hose, would have a smaller voltage. So voltage is like the pressure, and current is like the volume of water flowing. So a big hose has a lot more current than a little hose. So current is the amount of water flowing. And then resistance is pretty much how hard it takes for the water to get through. So let's just say you're spinning a water wheel, and the water wheel is all rusty and hard to push. That would have a lot of resistance. But if your water wheel that your water's going through is like oiled and has ball bearings, that would have less resistance. So the resistance is how hard it takes for the water or electricity to go through. And so greater resistance means it's harder. So now we're going to talk about Ohm's law. So here, before we talk about that, here let's just briefly talk about where voltage, current, and resistance comes from. And so in a circuit, the voltage is from the power source. So in this case, the voltage is generated by this battery here. So the voltage is all because of the battery. The battery's pushing the electrons. And another name for voltage is electromotive force. And that basically means the force that moves the electron. So greater voltage, it pushes harder, the electrons really want to move. Then there's resistance, which is measured in the resistor. So in a resistor, obviously you have resistance. So resistance is all from the resistors, these squiggly lines. And the current is the amount of water flowing through the pipe. So in an electric circuit, it's the amount of electricity traveling through the circuit. So if we took many batteries and with different voltages, so if we have different pressures, or the pressures of the electrons, and attached it to the same resistor. So if we just kept on changing this battery, we made it a 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, and then we measured the current, or I here. Another abbreviation for current is I, and which is measured in amps. We would get this graph here. And so voltage is on the y-axis, current is on the x, and then this line here, if it's flat, the slope of this would be resistance. And so this is known as Ohm's Law, which is V equals IR. So it's just like in algebra, Y equals mx plus b, but instead y equals mx. So the slope is m, which is the resistance, x is the amps, um, and then V is the voltage. So R is the slope of this line. And if a resistor is ohmic, that means it forms a graph that has a straight line when you plot voltage in amps. So if you keep on changing the voltage in amps, and you get a straight line, that means it's ohmic. So it obeys Ohm's law here, V equals IR. And this, pretty much everything we're going to do is ohmic, but if you get to higher level physics like in college or maybe even APC or something, you'll deal with non-ohmic resistors, and then you have to use calculus. And and by the way, volts is measured, or voltage is measured in volts, current is measured in amps, and resistance is measured in ohms, or this little symbol here that looks like an upside down horseshoe. So that's the units and what Ohm's law is, and we're going to be using this a lot. So in addition to Ohm's law, we have to know two of Kirchhoff's rules. The first rule is the junction rule. So basically, if a wire branches, the sum of the currents in each branch is equal to the original current coming in. So we have this little branch of wires here, so the current is flowing from left to right, so imagine it's going left to right, and it gets this branch here, and so it splits up, and so basically the current from I1 plus I2 must equal the current of I. So basically it's saying what goes in must equal the total current going out of this branch here, which makes sense because if you have water coming to a joint in the stream, so it's going around it like a little island, the water coming in and the water coming out on both ends must be equal, because otherwise, if it wasn't like that, either something's adding water at the joint or it's taking water. So it just makes sense. If you have a hose and you split up the hose into two sections, the water at both ends should equal the water coming into both ends. The second rule is the loop rule, and so the loop rule states that the sum of a voltage in a loop is equal to 0. So if I have a loop like this, a closed circuit, and I make a loop here, so this is my loop symbol here, the voltages of all the components, so the battery and this one resistor, equals 0. So the sum equals 0. And so in this one, we're going to do it so the sum of the voltage equals 0. So the 0 equals battery, the volts of the battery minus the voltage of the resistor. And so this is how the voltage is equal to 0, because some of them are positive and some of them are negative. So this is how it works. And I'll explain a little bit more when we do the next example right here. And so basically all I did was, because V equals IR, the V of the resistor equals to the current times the resistance of that resistor. So that's all I did here. So this is the loop rule, and then I just substituted V equals IR into this for this. And so now we have another loop rule. So this is a little bit more complicated. So pay attention here. So in loop one, so I drew a loop here. So this inside path, so follow my mouse, it go up to this corner through resistor 1. Then I go through resistor 2 here, and then I come out. So everything except this little thing on the far right. So in loop 1, the voltage of the battery, because it's adding to it, minus this voltage, which is voltage of resistance 1, and remember V equals IR, so I just replace it with IR, minus the voltage of this one, so I2 R2, I did the same thing, times its current and its resistance equals 0. So basically the voltage of this loop right here on this side equals 0. Now I'm going to do another loop within this parallel part. So these two lines just mean parallel. And by the way, I just drew rectangles with a slash through it to represent resistors. This is not an official symbol, but I just did it because on Microsoft Paint it's pretty hard to draw a squiggly line, especially when it's so small. So I just drew this rectangle with a slash. So inside this second part here, uh, 0 equals the voltage of a resistance 2 minus the voltage of resistance 3 or resistor 3. And again, I replaced it with V equals IR, so IR, so current of the second one times the resistance of the second one minus the current of the third one minus the resistance of the third one. And to know what you call positive or negative, um, you might be asking which one of these do you call positive or negative, because they're both resistors, so none of them are batteries. So in these, the outside one and the one before, the battery was positive, the resistors were all negative. But in these two, how do you know which one's positive and which one's negative? And the reason why is because of this little part here. If the loop and current are going the same direction, then batteries are positive, resistors are negative. So if, see this arrow is going this way, and this loop, I'm going to measure it the same direction, then batteries are positive, resistors are negative. Then, if it's the opposite, so if the loop is opposite of the current, then batteries are negative, resistors are positive. So here's the thing. So if the loop and current are facing together, so I'm going to say the current flows from the positive end to the negative end, and this is what most people say. So the longer end to the short end of the battery. So the current's going with this black arrow, and I'm measuring the loop from the from a clockwise direction. So since they're both going clockwise, batteries are positive, like this, and then resistors are negative. And then in this little loop, uh, you get the best of both worlds, because on one arm, on the right arm, they're both going the same direction. So they're both going clockwise. So since loop 2 is clockwise, this side they're going together. So resistors are negative. The other side, since the arrows are opposite, so R2, this arrow is going down, but the loop is going up. So this resistor is positive. So that's how you know which sign is which for the resistors. But it's not a big deal, but just make sure, again, you're consistent with what you do. So if you called the loop, or if you said the current went the other way, the signs would flip, but you should get the same answer if you did all the calculations. So always be consistent with what you do, but this is how you do it the standard way. So now we're going to talk about the individual types of circuits. So there's a series circuit here, and a series circuit has only one path from the positive to the negative terminal of the power source. So here we have a battery, which is our power source, and this is a positive end, and there's only one path for the electrons to go to the negative end. So one path only. And then, since there are no junctions, according to Kirchhoff's junction rule, the current is the same. So because there's no path for the electricity to move, all the water, or all the electrons have to flow the same way, so the current is the same throughout the whole circuit. Just like if you have a hose and there's no path for the water to exit, then the amount of water you put in is the same water you get back because there's no exit. So the current is the same throughout the whole circuit. So using the loop rule, so we just talked about the loop rule. So since these both these arrows are going the same direction, batteries are positive, resistors are negative. So the voltage of the battery minus the voltage of resistance 1 minus the voltage of resistor 2 equals 0. So this is what we just talked about. And so if we then further add stuff to that, remember voltage equals IR, so I'm just going to replace these two V's with IR of their corresponding resistance. So we know the current's the same, so that's why they both have the same I. And then this one's for resistor 1, so that's a different resistance. This is for resistor 2, that's why there's R sub 2. Okay, so now I'm just going to move both of them to the other side, so I just moved these two over, made them positive. And then instead of calling it voltage of the battery, I also replaced with IR, but instead of I called it IR R sub equivalent, so the equivalent resistance. So pretty much that's like the total resistance in this scenario. So equivalent resistance just means that you just like combine these two resistances, and I'll show you just in a second. So now that we have this, so total resistance equals the IR, or pretty much, yeah, IR sub total equals IR sub 1 plus IR sub 2. And since we know the current's the same, so I is the same throughout all of these, if I just divide by I, then I'll get this here. So this is pretty much saying the equivalent resistance, or the total resistance of the circuit, equals the sum of all the resistors. So that is fairly simple right there. It's what you would normally think. The total resistance is the sum of all the resistances. And so these are the two rules, or two things that are special about series. The current is the same throughout the whole circuit, and the total resistance is equal to the sum of all the resistances. So all you do is add it. And equivalent resistance, or R sub EQ, just means you took two resistors and you combine them to figure out their equivalent resistance together. So now we're going to solve a simple circuit here. We have to, so we have a circuit here with a battery with 6 volts. The electrons move from positive to negative, so that's why I have this black arrow here. Then it goes to resistance 1 with 15 ohms, resistance 2 with 40 ohms, and then it comes back. So we have to solve the circuit. So what we need is the current. So when you're solving circuit problems, be sure to collapse down the two resistors into one. So this is what I mean by REQ. So I'm going to take these two resistors and combine them into one. And since we know equivalent resistance is just the two resistors added together, so it's 15 plus 40, which is 55 ohms. So now that we collapse this down, the equivalent resistance of these two is equal to 55 ohms. So that's what REQ means. And so now we can use Ohm's law, because we only have 1, 2, and then we have the current left. So voltage and resistance. So to get current by itself, we just divide V by R. So first I'm going to plug them in. Voltage is 6, current is, we don't know, and then resistance is 55 ohms, and then I just divide 6 by 55 and get the current. And so this is all you have to do to solve a problem. So you first collapse down the resistors so that there's only one resistance here and just the battery left over. And then you just use Ohm's Law and solve like this. So series circuits are pretty easy to solve like this. But that's not all of it. So now we're going to talk about parallel circuits. So this is a little bit more involved, but still it's fairly simple. So don't worry. So parallel circuits have multiple paths between the terminals of the power source. So notice in this battery, we have two resistors right here. The current can go either on the left side through resistance 1 or on the right side through resistance 2. So there's two paths. So parallel circuits, if we remove one of the resistors, then there's still another path for the electricity to travel. So it's great. But in series, if we removed one of the resistors, there would be no path for the electricity to travel. So let's just say these are all light bulbs. So if you ever put up Christmas lights or any type of lights, like rope lights, string lights, if one bulb breaks and it's series, all the other bulbs will go off. So it's kind of frustrating if you're putting up series circuit bulbs and one bulb breaks and you have to throw away the whole thing. But if it's parallel, like nowadays you can buy parallel lights. They're so much better. Parallel lights have multiple paths for the electricity to travel. So if you're lucky, there might be still another path for the electricity to travel through, and just that one bulb goes out. So that's the difference between series and parallel. And so let's talk about using the loop rule. So let's use the loop rule inside the parallel component here. So we're going to loop clockwise, like this arrow here, inside this little square here. And so now that we know if the arrows are going together, so on I2 the arrows are going together, so that resistor is going to be negative. The other one, they're opposite, so that's going to be positive. Then we replace them each with IR because V equals IR. So the current of the first resistor times its resistance minus the current of the second resistor times its resistance equals 0. And then we move this negative to the other side so they're both positive. Looks nice. And let's just say we have identical resistors. So if we have identical resistors, the current will be the same. And since R and I are equivalent, both the sides are the same thing. And so then the voltage of the one path will equal the voltage of the other path. So this is one of our rules here for parallel circuits. So the voltage across a parallel component or parallel components is the same. The voltage is always the same. So the voltage in R1 equals the voltage of R2, and it'll always be like that. So this is one of the important rules. So now we're going to use the junction rule with current. And so we have the same scenario, two resistors with equal resistance. And again, V equals IR, and so now we want to solve for I, which is V over R. So, so now that we have V over R, now we replace every I in here with that V over R. So V over REQ, which is equivalent resistance. So let's just say we collapse these down into one resistor. That's REQ is the equivalent resistance of those two. So we have that, and equals V over R1 plus V over R2. And now now that we know voltage is the same in every single component, so these two components are in parallel, so these V's are all the same. So we can replace those all with ones, and so this is an interesting rule. The equivalent resistance, or the reciprocal of the equivalent resistance, is equal to 1 over the resistance of resistor 1 plus 1 over resistance of resistor 2. So this is kind of a weird formula, but if you ever did circuits and you wondered why this rule is like a reciprocal, this is why. Because we know the voltage is the same across, so now we use the junction rule solved with Ohm's law for V over R equals I, and then plug that in, and then we got rid of all these V's. So this is the second rule you have to know for series, or parallel. So this is the formal form of the formula here. So 1 over equivalent resistance in parallel equals the sum of all the reciprocals of the resistance. So now we're going to solve a parallel circuit, which is a little bit more exciting than solving a series. So first we have to collapse down the two resistors into a equivalent resistor. So basically we combine these two into one mega resistor to make the problem much simpler. So if we do this, we can easily solve for the current if we know the resistance. So this is where Req comes into. So 1 over Req equals the sum of all the reciprocals of the resistors. So 1 over Req equals 1 over 20, because we have 20 ohms here, plus 1 over 30. We have 30 ohms on the other side. So when you do this math here, instead of making common denominators, my teacher taught us that if we just cross multiply, so 30 times 1, 20 times 1, over the multiplication of the two denominators, so like 20 plus 30 over 20 times 30. So it'll always be these two numbers added together over the multiplication. So equals 1 over Req. So that's a much easier way than worrying about common denominators and stuff like that. So then if we flip the fraction, so if we flip both sides, 1 over Req turns into Req, 50 over 600 turns into 600 over 50, we will get 12 ohms for the equivalent resistance. So now we know this equivalent resistance is equal to 12 ohms. So these two together only have a resistance of 12. Now we use Ohm's law, so V equals IR, and now we want to solve for current, so we do V of the total voltage over the equivalent resistance equals current. 9 over 12 equals 0.75 amps. So now we want to solve for both the currents in the parallel component. So so we solve for the total current. So this is the total current here, this big black arrow here. And so now we want to solve for these two branches, the currents. So now we know the voltage across the parallel is 9 because which rule which phrase did we learn, or what did we learn that says that? And so we learned because they're parallel according to the loop rule, or remember we derived it that parallel components have the same voltage across, and so even if we did solve it, you just say that, and then because the battery is 9 volts, the other side has to be 9, so they subtract to 0. So parallel components, now that you know, have the same voltage, and since it's only hooked up to one battery, it must be negative 9 volts here, or pretty much 9 volts, but opposite. So now for each of the resistors, we have to do Ohm's law. So V equals IR, so V over R equals I. So the voltage of the parallel part over R1 equals the current in R1. I mean, yeah, current of R1. So 9 over 20, because 9 volts over 20 ohms equals 0.45 amps. And the other resistor, the voltage is still 9, resistance is 30, equals the current in there. So 9 over 30 is 0.3 amps. So notice that the junction rule is still obeyed, because remember the junction rule says that the current in equals the current out. We know that the total current was 0.75, and we know that the currents in each branches was 0.45 and 0.3. So if we add those together, it does check out to be 0.75, which does obey the law. So that's kind of cool. And the great thing about if you have parallel circuits is the electricity will always try to go to the path of least resistance. So notice that when we solved, more of the current went through the 20 ohm resistor than the 30 ohm. And this will always be true. So if you're doing a problem and you want to know if you did it right or not, you can check the junction rule, and you can also make sure make sure that there's more amperage in the resistor with less resistance. So it'll always be true, and so the path with least resistance will always have more amps or more flow. So thank you for watching my physics video today. And so today we learned all about circuits, and we introduced the rules about them, and we solved maybe like 2 problems. So tune to the next video to learn about solving more complex circuit problems. And if you enjoyed this video, please spread the word and like this video. Tell your classmates where you're going for your physics help, and email me any questions you have about circuits. I know when I first did it, this is like the first time I was solving with it, and so I was like, my teacher was going so fast with this stuff, so it took me a while to get this. But after you do a few problems, you'll get it. Try to do these problems you have here by yourself to prove that, so you can practice it and know it until you got it. And practice deriving those rules that I showed you. So just pause the video right before it, try to derive it, and then check your answers by playing the video. So if you're taking chemistry, please visit my chemistry tutorials, buccaneerchemistry.weebly.com. And thank you, and I hope to see you next time. Bye-bye.